All right, so exam one is done. Exam one is taken by you. I have not graded exam one yet. I'm behind. I have lots of other exams and classes to take care of first. Let's see, and then I'll get to it. We are still on proof. Okay, so we're still have a few more chapters that cover proof, and proofs will just for a while will just get more sophisticated. Then we will get to truth tables, which is easier, always easier. So that'll be kind of a break, kind of a relief. Then near the end then after truth tables, we'll get back into, I guess you could say, tougher stuff. All right? So it's going to get kind of progressively tougher now, okay? Although, maybe not. If you're already caught up on proofs, you're comfortable with proofs, then I wouldn't say it's tougher, okay? But if you are a little bit behind, then it's going to be some catching up to do, okay? Then there's going to be a little bit of a relief, and then it's going to kind of kick up back again, all right? So, yeah, just to tell you about the way I set up this class, I do proof in the first part of class, whereas most logic classes do truth tables and kind of the easier stuff first. Then they get into proof, okay? I like to do proofs first. One reason is that students at the beginning of the semester are generally paying more attention. They have more time to read and stuff like that, right? They're maybe a little worried about how the class is going to go. So they put in that work, that necessary work to get proofs done. Yeah, if you start proof like halfway during the semester, that's when you get a lot of attrition. A lot of students going like, wait, I'm not ready for that. Wait, this class was like straightforward, pretty easy, something like that. Okay, so yeah, and also you don't have to do truth tables first. You can do proof first. The idea is going to be this: we're going to do proof, get that basically done, then do truth tables, which show that our rules work. Okay, that show that our system works. Okay, so that's the approach there. Okay, today we're going to look at a famous technique for doing proofs. Okay, the book calls it a rule of inference. I call it more of like a proof strategy, or an approach to a proof rather than a rule of inference. But it doesn't matter really what you call it. It is a very useful tool for solving certain kinds of proofs. Okay. When you want to prove the truth of a conditional statement, if that's your target, then the strategy we're going to learn today is super helpful. It's called conditional proof. So let's get to that. Conditional proof. Let me write something on the board just really quickly here. Just a couple of words. Okay. All of our proofs so far have been direct. I'll tell you more about what this means as we go, but this is our first proof strategy or method of doing proofs that is indirect. Indirect. Okay. One way to understand the difference is that in a direct proof, all you do is you use the premises given, apply the rules to the premises given, and then get your conclusion. So all of the proofs we've done so far have been direct in that sense. In an indirect proof, what you do is, yeah, you take the premises, you accept the premises, but then you make a supposition. Like, oh, I suppose something else is also true. Okay. See right here? You're going to suppose something in your proof. You're not saying it isn't actually true. You're not saying it is in fact true. You're saying suppose it's true. So that's the mark of an indirect proof. A supposition will be made. Okay? Let me just talk through conditional proof. If your goal is to prove a conditional statement, which are all of the forms circle, arrow, square, what you do is this. You suppose circle is true. That is, the antecedent of the conditional is true. You suppose it to be the case. You're not saying it is the case, you're supposing it to be the case. Then you use your rules to derive square, which is the consequent of the targeted conditional. Then on the final line of your proof, okay, you conclude, hey, if circle, then square. Because isn't that what you just did? You suppose circle. If circle, then square. Then you conclude circle, arrow, square. So that's what conditional proof does. All right. So without examples, though, you might be going, what? I'm not sure what this means. Okay, we need some examples. Okay. But I want to tell you generally what conditional proof does. Well, I've written it up right here, but what I'm going to do is this. Let's do a proof, then go back to this page. Okay? Because this is a write-up of what conditional proof does. And it probably looks more complicated than it actually is. All right. So we can go back to this page. Okay. All right. So, say you want to prove A arrow B, B arrow C, therefore B arrow C. Sometimes that's called transitivity. Okay? If A equals B and B equals C, then A equals C. That would be transitivity. Okay? All right. Let's see. And this is just, I guess it looks just intuitive, right? A leads to B, B leads to C, A leads to C. Okay, so say you want to prove this. Say you want to prove this. So before we do the proof, look at this. Your target is A arrow C. So that means your target is a conditional statement. And conditional, I'm just going to have you do that. Look, let's go back to the original thing right here. We want to prove A arrow C. So what you do then is suppose that A is true. You suppose that A is true. Go back here. So in your proof, you're going to suppose A is true. So let's do this. So here's how you start it off. A proof of transitivity here. So you have two premises, A arrow B, and then you have B arrow C. Your target is A arrow C. So, and we've already basically said it, but let's just make it clear. what goes in for line 3?
Suppose
Suppose A. Now, you don't use the word suppose. You just put in A. Okay? However, when you suppose something is true, you're not actually saying it's true, you're just supposing it's true. Okay? You indent. And that's telling the reader that you're not really saying it's true. Like if I said, oh, suppose Trump won the election. Am I saying that Trump won the election? No, I'm not. Okay? In the logic proof, to tell the reader that you're supposing something to be the case, you indent. Okay, I'll show you what that looks like. So right there. Can you see that? I don't want to give too much away right now. Okay? So what you do is this. See I indented here? 1 and 2. See, 1 and 2, I'm saying are true. So they stay on the left column. When I make a supposition, I indent. Again, that's telling the reader, I'm not committed to this. So when you do a conditional proof, make sure you indent. Okay. Actually, that's a mark of an indirect proof. Indirect, right? So what this says right here, this is just code, I guess, right? Sup means a supposition. Suppose, and then /CP. And then what that means is suppose for the sake of conditional proof. So you can just read that out. Sup CP. Sup CP. Okay, now before we finish the proof, what conditional proof kind of does for you is give you an extra premise for free. Okay? 1 and 2, you have the truth of, you're committed to, you're cool with those, and those are solid. And then what you do is, well, suppose we also have this. Okay? So imagine you're making like a cake or something, I don't know, and you have a couple of ingredients already. You have flour and what else? Sugar. And then you go, well, suppose we had pineapple too. What could we make with that? It's like that. You know, you don't have the pineapple, but you're like, suppose we have pineapple. Okay? And that opens other doors, doesn't it? Because you're like, whoa, if I have pineapple plus, whoa, I had those original ingredients, I can do a lot more now. So that's what a supposition gives to you. Now, you don't really have the pineapple. You don't really have A. But you say, what if I had A? Well, what can I get? Okay. All right, I'm going to pause. How's that so far with this? Okay. Well, you know how to deal with these 3 things now. Before we do the rest of the proof, just talk through it. Now you add that ingredient, so to speak. You add that supposition. What can you now do with everything you have? What can you now do? I know last week, exam and stuff, nothing over the weekend. Joaquin?
Derive B.
You could derive B. Good, with 1 and 3. Right? You're going to get B by itself. What else can you get? You Winston.
Then you get A to C.
What? Well, not yet. Okay. If you have B, you can get,
There.
well,
C.
you just get C. Right? If you have B, so if you had A, you can get B. And then when you have B by itself, you can get C. Both using modus ponens. So double instance of modus, double usage of modus ponens. So you're going to get C on its own. All right? Now once you have C on its own, then you can say, hey, if I have A, I can get C. It's like, hey, if I had pineapple, I could get, pineapple upside down cake or something. So here's the proof. Okay, we're going to have to talk through this a little bit. So now you have that supposition, which is kind of a premise for free. It's not a true premise. It's kind of acting like a premise. Okay? Now if you have A, you can get B, 1 and 3 MP. And if you have B, you could get C, that's 2 and 4 MP. Now, you have this indented proof. You could call it a subproof. In that subproof, you've gone from A to C. So then you can tell the reader, hey, A gives me C. Now you can leave the subproof and say for sure that C is true. Sorry, that 6 is true. You don't know whether C is true. You know 6 is true. If A, then C. Okay? That's Cindy.
For lines 4 and 5, even though they aren't suppositions, why are they indented?
Okay, good question. Why are B and C indented? Anybody want to answer that? Yeah. Hunter.
They aren't necessarily true.
Well, they aren't necessarily true. Why? Because they both come from the supposition. They rely on the supposition. Okay? So because this is kind of, I guess you could say iffy, it's a supposition. Anything that relies on that supposition is also, I guess you could say, suppositional. Okay? So it's like, if you have pineapple, then you can do this thing, you can do this thing with the pineapple, but they still rely on the pineapple. Okay? But then in the conclusion, you could say, I know, mixing these metaphors or whatever. The conclusion, you could say, if I had pineapple, then I could do this. Okay? So 6 does not rely. Okay? It doesn't, right. For 6 to be true, you don't need 3 to be true. But for 4 and 5 to be true, you need 3 to be true. Does that explain it, Sydney?
Yeah.
Because 6 is just conditional. If 3 were true, whereas both of these, 4 and 5, right, for them to be true, 3 has got to be true. So that's the difference. That's the difference. So this move from 5 to 6, when you leave the indented world, right, the indented part, when you break out of the subproof, that is technically called discharging the supposition. Sounds like a medical term or something, I don't know. So you discharge the supposition. The supposition was 3, and you discharge it in line 6. So I've been calling it, we've been proving there's some kind of transitivity happening here. But it turns out we have a rule of the form A arrow B, B arrow C, therefore A arrow C. It's called hypothetical syllogism, HS. And you were allowed to use it on homework 3. I don't know if maybe 1 or 2 people did. But now we've proven that it works. We've proven that rule. So now we have a new rule, HS. Okay, so let's talk about what, let's kind of label this proof here. I think I do it on the next slide. Well, that's hypothetical syllogism. Circle, arrow, square, square, arrow, triangle. If you have those two things, you get circle, arrow, triangle. So that's HS. Right. Okay, I'll get this. I'm going to go back to here, kind of read off the proof. Okay? So this is kind of writing up the whole proof. Say that you want to prove that a conditional statement is true, and what we're trying to do is prove A arrow C is true. What you do, first you suppose the antecedent, so that's A, of your targeted conditional is true on a separate indented line using the justification sub CP. Sub CP. Second, from this supposition, together with the premises, derive the consequent square. So this is just a write-up, a technical write-up of what conditional proof does, what you do in conditional proof. Third, if successful, you can infer that the target conditional, circle, arrow, square, is true. By doing so, remember that was line 6, by doing so, you will discharge the supposition. Okay. All right. This is a pretty, I don't know, it's a pretty nifty little strategy. It always works when you try to prove a conditional, assuming the conditional actually does follow. Right? But if the conditional actually logically follows, conditional proof will always work. So it's a super handy tool. Sometimes it can be very hard to directly derive a conditional statement. Extremely difficult. Conditional proof is worth learning because even though there's a little learning curve to get conditional proof down, it's going to make a lot of future proofs a lot easier. Super useful tool to use. Oh, yeah.
So before you had hypothetical syllogism up on the board, so do you need CP for HS?
Well, what if I said, let's see. What if I said you're not allowed to use HS? Prove transitivity. Then you can do it without HS.
Okay, so they aren't like reliant upon.
They're not reliant. Yeah. Well, so you could prove. In a sense, you don't need HS.
Okay.
Yeah. But now what we've done is since you've proven it, now it's a super handy rule. You can use that rule, so you don't have to use CP anymore if you want to do hypothetical syllogism. And we're going to do that with some other rules too. Once you've proven those rules, they're good to go. We can use them now. Yeah. Let's see. Go back to the proof. So any questions about this proof before we go on? This proof here. Okay. I'm watching the laptop battery. Might have to run at some point and get the charger. So it's at 50% right now. Going way too fast. Okay. Yeah, Marcus.
About formatting.
Yeah.
Do you have to like draw the line, or is it just like indenting? And
You don't have to draw the line.
Okay.
I do because I tend to do that because to make it clearer. Also, I can do it with Keynote, whatever I'm using, so I might as well.
Sure.
But you could add your own style there. This not super picky about that. However, you've got to have somehow separate that out. It shouldn't look like it belongs to the same column as the other numbers. So that's quite important to do it that way. There are other ways that other logical systems use without indenting, but what they do, they add another column of numbers on the left, like this, that talk about the assumptions being used. And teaching that kind of proof is a nightmare. It sucks. You don't even need it. So it's easier to indent it, right, than keeping the track of the assumptions. We haven't even talked about assumptions, really. Like another concept, you don't really need that here, okay? Because actually the proof system has become better and more streamlined over the years. Yeah. When I first learned proof, it had that other column. It's much harder to teach and learn. Yeah. This is a nice streamlined system. Okay. All right. Okay. Actually, yeah. This might give me time to get the charger. Okay. Start doing this. It might go pretty fast, or it might not. But just see how far you get on that. You might have to look at the rule of conditional proof. Go back to it, or your notes, or the book itself. But I need to. I'm gonna run out of battery here unless I go and get the charger. Go to IDC. Back pretty soon. right, time to talk about it. See if that's charging now. There we go. Okay, so the target is a conditional statement, not P arrow Q. What do you suppose first? Not P. You're gonna make a supposition. So you suppose not P. Then that needs to be indented because you're not committed to it. You're not saying it actually is true. Okay. So if you have not P, what's the next step? QDS, okay? Actually, this is pretty quick, isn't it? If you tried to do this another way, it could have been quite difficult. The other way to, we're kind of doing with this is we're proving the rule MI. At least one direction of that rule MI. Joaquin, you had a question?
Oh, no, even
Okay. So we basically did the proof. Let's see, let's do it here. Okay. So here's a proof with annotations. So here's the premise, one premise, the conclusion, not P arrow Q. You suppose the antecedent of the target conditional. The target conditional is not P arrow Q. You suppose the antecedent is true. Given that extra ingredient, so to speak, you can now combine it with the original premise using DS to get Q. Now you can tell the reader, hey, from not P, I can get Q. And so what you do is tell the reader on the fourth line, not P arrow Q. And then you say 2 through 3, CP. So the supposition in line 2 is discharged in line 4. And that's something I haven't talked about before, which means it can no longer be used. Okay. You can't just go from this and then use this again to get something else. You can't do that. You kind of used it up, so to speak, right? You suppose it to be true, and then you've discharged it no longer. Now you could always suppose it again. You could do that. Winston.
Just a small question. So I just put like 2 comma 3 instead of 2 like through 3. Does that matter?
It doesn't matter, but usually it's going to be
Yeah.
more than 2 lines.
Yeah.
So that's why I do the dash. It could be extended. Just like the prior proof, there were like 4 lines there, so it made sense to have the dash. And here it doesn't matter which one. You might say, well, it's weird to have a dash, but I don't care. I don't care. And then you say CP, because that's the sort of proof you use. Suppose it for CP, and then you say, hey, I just did CP. Any questions about this one? Conditional proof. Okay. Let's try another here. Let's talk about it. Yeah, the last one I guess I could have had somebody scroll to this slide. Yeah, that would have been good. Okay. So the first thing to notice is that it would be difficult to prove this correctly, given our other rules. CP opens the door to get this thing done. So the target is A arrow not C, so that is a conditional, so you can use conditional proof. What will you suppose on your next line? A. Because A is the antecedent of this conditional. So you suppose A is true. And then you want to indent, so you have A by itself. Now if you have A, just by looking at this proof, I know some of you are already working on it, right? But just looking at this proof, if you have A, what can you get? B. Now, if you have B, we can just talk through this proof. If you have B, what can you get? A and B. And then if you have A and B, you'll get not C, which was the target consequent. Okay, this is the consequent you wanted to get, or square. You got not. So you got not C there. Then you could say from A, I got not C. So what we did right there is kind of talk through the whole proof. And are you able to write that down? Here we go. Writing down what we talked about. Suppose A, for the purpose of getting not C. Once you have A, you're going to get B. And then, right, A and, well, can't you get A and B together, right? But that's just the antecedent for not C. So you get not C, line 6. From A, you get not C. Therefore, A arrow not C. Any questions about this, how it's written up, how the proof is done? Yeah, Nate.
Is you always suppose the antecedent first?
Yes.
Before the. Just making sure.
Well, you can. I mean, if the other things you can do, you can do other things first. Whatever you can get done. But
That's
right
what
now,
I'm
with 1 and 2, you can't really do much.
Yeah.
I use the pineapple cooking metaphor. Right. If you have if you have the ingredients like flour and sugar or something, and if you add pineapple or something, right, so you can use that metaphor. But I also sometimes use a party metaphor. So imagine lines 1 and 2 are like people already invited to the party. So think of like A arrow B, that's like, group of people or something like that. And then the second line also represents people at a party, right? And then don't you sometimes do things like this? What if I invited Alan? So that's A. What if I invited Alan to the party? Suppose Alan came. And you're thinking about it, go like, well, if Alan came, then B's going to happen, right? And if B happens, A and Alan and whatever B, I don't know. Beatrice will be mad. I don't know, something like that. Okay, A and B. Oh no, and if A and B are true, whoa, you're going to get not C. And so you can conclude by saying, well, if we invited Alan to the party, we're going to get not C. That's the way conditional proof works. Again, you never did invite Alan to the party. You're like, you don't even plan to invite Alan, ever. But you can still say, if Alan came, then certain things will happen. Cool? You're like, what parties? It's COVID time. So I know it's kind of fake and stuff. But there will be parties eventually. There is philosophy club today. It'll be outside, so it is kind of like a party,
You have to pre-sign up for that, or can you just show up?
Just show up.
Okay.
So it's at the Bagish Overlook, which I think is kind of like that amphitheater kind of thing on the West Campus, on the lawn. Okay. Yeah, you could just show up. You don't have to sign up. There's no membership fee or anything like that. There's no right of initiation, at least as far as I've seen. There may be one in the future somehow. Okay. Questions about this proof? Zoe.
Not specifically about this proof, but
Okay.
when we're doing, when we're like making like our own premises and stuff like that from like a paragraph,
Oh,
is there gonna be like a line within like that paragraph that like says like suppose like if blah 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 that where we know that we're gonna have to use CP?
oh. Well, often CP is just used to prove it might the supposition. Suppose A might not be in the proof itself, like in a natural language or narrow language proof. But if the conclusion is a conditional statement, you can always do that as part of your proof. However, in real life, arguments do have suppositions. They often have suppositions. Let's see. I mean, if you argue about politics, people do things like, oh, suppose Trump won, or like with the fire, like suppose the wind changed direction. I mean, and we do that stuff all the time. It happens in physics. Suppose the Earth didn't rotate, or suppose the Earth rotated at this speed, at this velocity, and it increased or something. So suppose that kind. Let's see. So we argue that way all the time.
Okay.
But in the original argument, maybe you just had 1, 2, and the conclusion. Maybe you have that. But when we're trying to prove that it's valid, we could do it this way. Any other questions about this one? Good. Okay. Okay. I really want to make sure you learn conditional proof, so we're going through different examples. So, we have one premise, and then we have a target, and the target is a conditional statement. You see that it's a conditional statement? FNG arrow H. Okay. So, in a conditional proof, you suppose the antecedent is true. That's circle. What is circle, in other words? What is the antecedent?
F and G.
What was that?
F and G.
F and G. F and G. So I'm just going to write this down right here. So you have F and G. What is it? Arrow H. This is of the form circle, arrow, square. So what you're going to do is you're going to suppose circle. So whatever circle is, doesn't matter what it is, it's going to go in here. So what you do is then suppose F and G. You don't have to overthink it or like that. Just go like whatever is in circle should be supposed. So just on your own for like a minute or two, what will be the next step after that supposition? Or the next couple of steps? Anybody want me to look at what you're doing? You're not sure where to go with this. Anybody want me to come around and just see quickly what you're doing? Me. Okay, so yeah, good. Actually, let's see. Then look at what you can do with premise one. John, did you get the next line?
Like
So you're writing that down.
I wrote this down to say that I don't get this was on the previous line.
Oh,
Like, how can A and B get C and then A by itself get C? Like, wouldn't these values be different? Like, 'cause whatever A is, if you're adding B to it, shouldn't this be more than just A by itself? Like, this was the previous one. I was going to ask you about this.
okay. Let me look. Yeah. Well,
So,
what you don't want to do is this. It sounds like you're doing it. You are using your intuition to see whether it's even valid. These are all valid. Trust that they are. Don't overthink it. Just follow. What I'm actually teaching right now is a mechanical procedure. It's literally just memorizing steps. But the key is knowing when to apply it. But when you're doing like, I'm not sure how is B going to follow? What you do is just do it, and then it happens. If you follow the procedure.
okay.
If you start overthinking it, you're going to go in logic. Because we're able to show that the weirdest things are valid. So if you use your intuition on it, it's going to take you in the wrong
It's
direction.
definitely not mathematical. Because, like, I was thinking with n value plus this value,
Yeah, you cannot think, it's not analogous, it's not isomorphic with mathematics. It doesn't line up with mathematics. You cannot think of the operators the same way. Now, there are some similarities, so that's why you can think it goes straight. You cannot get into the game of like, is it similar to math? This looks like a math, rule or something. You can't do it that way. The operators are different. Because in math you have operations of addition, multiplication, division. Here you have operators of conjunction, disjunction. They all operate differently than math ones. So you're going to get very weird results if you start, or you're going to second guess yourself if you start thinking it has to match math. You can't think that way. Okay? Winston,
I just want to see.
we want to look at the footprint. Yeah.
I don't know.
Where are you at here?
Right here.
This one. Okay. So now you have these extra.
Then
Wait. No. 2 cent. Oh yeah. Okay. 2 cent. GH. You're skipping a step. You also need to simplify F by itself.
okay.
So let's. Yeah. Okay, good, you got that. You don't need to do another supposition. When you simplify it out about F, you should also simplify it about G. Okay.
Sorry, so how would I join this together? Because I
So you have F. Actually, this is all perfect. You haven't finished it yet, though. So what's the issue? You just have one more line.
Yeah, so I was just wondering because I was thinking like orange because I have the F and the G and the H, but then the A and C it's comparison to the premise of it. Like you can't see and maybe that would be that.
Yeah. Look at from 2, you get 6.
Sorry.
You're done.
Yeah, okay, yeah, I remember.
Okay,
Thank
you are done. Let's do this proof. Okay? So without overthinking it, you just suppose the antecedent of the target conditional. Don't even, if you think into it, you're going to second guess yourself. Just do it. F and G. So next line, that's going to be you're going to indent, you're going to write FNG. So, let's see if I can show you. So right there, you suppose for CP, FNG. Okay. Now, what you can do, before doing anything else, you could just, if you have a conjunction, just simplify it. Just get F and G on their own. You don't even have to like think right now of getting a vision. Just do what you can, and F and G will be had. Let's see if I do that next. Okay, I did not do them both at once. I simplified as I needed them. Okay? It turns out you need both F and G on their own. Let's just do F by itself. Just gonna follow the way I did it here. Now, if you have F by itself, combine that with premise 1, you have modus ponens. That's circle, arrow, square. F is circle. So you're going to get G, arrow, H. You're going to get G, arrow, H. And you don't have to think about how is this ever going to get here. Okay? Right now, just do what you can. Now you have G, arrow, H by itself. It turns out that you can get H pretty fast after you bring down G. That's also a simplification from line 2. You could have just done these 2 lines right away. Just break that apart. Remember the Lego analogy? It's like if you have a Lego pieces in a block all together and you need to make something else out of them, the first thing you do is just take it all apart. So this is like a block of Legos. Take it all apart. Take it apart here, take it apart here. Okay. Now, you have G, arrow, H. Now you have G from line 2. So now you have modus ponens again. You can get H on its own. So you get H from 4 and 5 MP. Get H on its own. Now, you have achieved, haven't you, the conditional. If F and G are true, you're going to get H. It's like if I invited Fred and Ginger to the party, okay, Harold will be glad. I don't know. There we go. You get H. So then you say it in the final line. If F and G, then H. If F and G, then H. Which is your target. If you try to do this any other way, given the rules we already have, you either can't do it or it's a beast. So, again with CP, just kind of learn the technique, you learn the method, and the other part of that, learning the method, but also part of learning the method is when to apply it. You apply it when you're trying to prove a condition. Okay. That's kind of a good way to remember when to use conditional proof, is when you're trying to prove a conditional. Okay. Then just follow the technique or the method or something, right? Suppose the antecedent. And then use that supposition to derive the consequent. How does that proof look? Okay. Okay. Let's look at another one. You see today, I reserved it for one thing, right? Conditional proof. It's such an important thing to learn. Such an important thing to learn. So, look at the first one there. See that F arrow, G arrow, H, and then that leads to F and G arrow, H. It turns out you can prove it the other direction as well. The other direction. So, this is going to add another element. Okay. It's going to add a little bit of complexity, but no added rules, no added. It's just you follow the same guidelines. It just turns out you need to do it more. You'll see. You'll see. Okay. So the target is a conditional statement. What is the antecedent of that conditional statement? I heard F. Just F on its own. So indent, but line 2, F. Now, I'm going to write that second. I'm going to write the second one down here. So here we have first line. We have FNG, arrow H, and then a line 2. You suppose F. Okay. Now, in the other proofs, when you added that supposition, you were able to do things with it. Okay? So go back to the pineapple metaphor. You have those two ingredients, you add pineapple to it, you can make something with it, right? Or using the party metaphor. If you invited Alan, oh, then Alan interacts with the other people there or whatever. Right? Something happens. And you see how that happens. The problem here is that you add F, you have nowhere to go. So you might be tempted to just stop the proof and say this is invalid. If you think about it, like John, you were like thinking about it, like kind of like intuitively, you'd probably say something's wrong with this proof. You might be tempted to, like but then you need to kind of take a step back and go, what does conditional proof tell me? It tells me whenever I want to derive a conditional statement, I can use conditional proof. Whenever. So, do you know what I'm getting at, Joaquin? Get a
So you could suppose G also.
There you go. Okay, so let's back up. So you supposed F. You're at this stage, and you can't do anything. But what's your goal? Well, if you have F, your target at the kind of intermediate target is G arrow H. Well, what does conditional proof let you do? Anytime you have a target conditional, by the way, it doesn't have to be your conclusion. Anytime you want to derive a conditional statement, I don't care when it is, you can use conditional proof. So now your target is G arrow H. It's this intermediate target. Well, that's a conditional statement, so you can suppose G. And every time you make a supposition, you indent again. So let me show you how the proof looks, at the start at least. Check this out. This is cool. I think it's cool. So you suppose CP, and I add something here. You tell the reader what your target is at this point. This helps you do a proof. The book doesn't do this. So now that's your target, which is itself a conditional statement. So if your target's a conditional statement, you could always suppose the antecedent, which is exactly what, as Joaquin said, it is G. Look at that. Check that out. So now you have line 1, and then you have a supposition, and then you have another supposition. By the way, you can keep on supposing all day long. There's no rule against that. You probably don't want to. Like, can't you do it? Like, if you're arguing with somebody, you could easily make a couple of suppositions, right? Suppose the fire shifts direction. Suppose the wind picks up. Suppose you can add suppositions. There's nothing wrong with that. So now you suppose G for the purposes of getting H. But now it's doable. You've added enough stuff to now you can actually generate new lines. And really, I'm glad John asked that too, right? Because don't start overthinking this. Like, oh, they're both indented, it's not gonna work out right, or something like that. You can easily get caught up in that. You just follow the procedure, it actually works. It all works out. It's like kind of shocking that it works. If you have F and G, you can now use conjunction. And then you get F and G on their own, now you can get H. Once you have H, then you can get G arrow H. And then once you get G arrow H, you can get F arrow G arrow H. So there's going to be two conditional proofs. One is embedded in the other. Check it out. Here's the proof. I think for teaching purposes, Marcus, it's good to have lines, because you can kind of see that, or you could have like brackets or something, to separate out the proofs. So now we're at line 3. If you have G, you can combine that with F to get F and G, 2 and 3 conj. Now if you have 2 and 3 conj, you can derive H, 1 and 4 MP. Now look at this. From G, you got H, so you can discharge the supposition at line 3 to get G arrow H. But now look, line 6 came from line 2. See, they're lined up there? So from 2, you can get, right? From F, you can get G arrow H. That's 2 through 6 CP. And see how there was this like inner CP in this one, embedded CP in that one? So it might not look like it's going to work out, but then while you're doing it, it works. It ends up in the right place. I can see how people argue this way, like, well, suppose F, well, that leads to G arrow H. Well, let's suppose G. Well, let's also suppose G. Yeah. Thoughts about this proof here? Okay. Let's see. I'm not going to pass out a homework assignment today. I will pass one out on Thursday, and it'll be due the following Thursday. It's going to be about proof. Okay. So if you are still not comfortable with proofs, like this is like, whoa, keep going to the tutor if you haven't already started going. Keep going to the tutor. Go over problems again. With logic, just like with language, the more exposure you get to it, more exposure you have, the better you're going to do. Just keep on doing this stuff. And there's a learning curve. It can be tough, but just keep on working at it. Let me think if I have anything else that I wanted to cover on regarding conditional proof. No, I didn't. And this could be enough information right now. We're ending with a pretty sophisticated proof for this one. Any questions or comments about this or conditional proof in general? You'll definitely be using it, and it's very, in the rest of the course, especially when we're doing proofs. Okay? Any final thoughts or questions about Joaquin?
Could you try to say that?
You mean like an English language version of this? I could make one up on the spot, but it'll sound probably silly. Just you need to plug something in for F, G, and H, have a dictionary, right? So, let's see. Let's see. If frogs and what's a reptile that begins with a G?
Gecko.
Wait, what?
Gecko.
Gecko. If frogs are reptiles and geckos are reptiles, then what's true of reptiles? Then Joaquin, what do you want to say?
Cold-blooded.
Then they're cold-blooded. Okay. And the idea is that if that's true, then it should also be true. It should follow that if frogs are reptiles, then if geckos are reptiles, then they're cold-blooded, or something. Then then they're cold-blooded. The thing is, Joaquin, I'm not sure why you asked me that, but sometimes like this, it doesn't really track the way we speak in ordinary language. I mean, do you really talk that way like this? Sometimes you do, but it's pretty rare. But it turns out that it is equivalent to that because we proved it in both directions. So even though it's awkward and weird, it's still logically equivalent. So that's something.
The last one felt easier to think about in English.
Intuitively, and yeah. Some of these are not going. They're going to actually. You raise a good issue. Is that our notion of the arrow of conditional statement? I haven't really done this yet. I will later in the semester. It does not track 100% ordinary usage. It is often called paradoxical. It has a truth functional purpose. It has a purpose in logic. It is not meant to track real life meaning. So when I'm very careful when I say they are logically equivalent. I don't say things like, oh, they have the exact same English meaning, because I'd be wrong about that. But logically, they mean the same thing, which is different from saying they have all the same connotations in your ordinary language, which they don't sometimes. When I do truth tables, I do talk about the paradoxes of our use of the conditional. There's actually an appendix in the book that's very well done that talks about the paradoxes. And it's actually the case that every logical system engenders certain paradoxes. And when people choose which logical system to follow, they tend to choose the one whose paradoxes they can live with. But I'll also try to argue that there's actually something intuitive about the way we do it as well. So it's kind of good and bad or something like that in sense. There's something intuitive about what we do too. So I'm going to be arguing that as well. Yeah, so you raise a good issue. Some of these cases, it's not going to feel right, okay? Right. But we're trying to understand the logic. We're not trying to understand exactly what people mean. That's a different thing. That's more like this. That's more like the study of rhetoric, I guess, rather than the study of logic per se. Yes, that's one way to look at it. Or like if you take an English class, it'll talk about all these other meanings beyond the logical. Whereas in this class, we focus on the logical meanings. Okay. All right, that's cool. Anything else? Any other questions or comments about this? Winston,
So when does hypothetical syllogism come in? I was just wondering.
when does it come in?
Are we going to use that, or are we going to use?
No, we're going to use it now. Since we've proven it, it's good to go. We can use it. Yeah. We don't have a rule for this, so you need to prove that again. There are other systems that call this right here exportation. But our system does not have it. Exportation is a principle in logic, exportation. But it actually is this rule, but we don't use it in our system. Some systems do. We don't need to use it partly because we can just prove it. So, but you can always add it to a system. Exportation. Zoe.
On like tests and homework and stuff, is it specifically gonna ask us to use CP, or are we just gonna have to like look at the proof and like just like come to terms with the fact that like nothing else works?
Well, usually, most of the time, I'm not going to force you to use a particular rule. So you kind of learn when to use it. Now, I'm going to give you little later on. I'm going to consolidate and give you a handout of all the proof strategies we've covered. Okay. Sometimes, though, I may, like in a homework, say something like use an indirect proof, and we're going to learn one more indirect style of proof. And so that one, you'd be like, okay, I got to use conditional proof, or the other one we'll learn. Yeah, but generally speaking, you do what it takes to get the proof done. And part of that is like figuring out which proof method style you want to use. Cool. Anything else? All right, hope to see some of you or all of you at Philosophy Club 4. Beyond that, I'll see you at on Thursday. Okay, stay safe.